Okay, guys, good morning. I hope you're all doing fine, you're good, you're healthy. And today we will continue with, let's say, introduction chapter kind of. If you remember, we were discussing the fundamentals of computer science, and the first phase was about mathematical proofs. And I said many times that this is highly important, since throughout the semester we will be going through many algorithms, many different, let's say, specific equations, and we will also cover the proofs of them. So it's better you learn the fundamentals, and then it will be easier for you to understand what is going on during the proof of other algorithms and equations. And let me remind one thing, an important thing: if you're undergraduate students and have courses from first, second, or third year, you cannot take this course. You can only take 533 if you're undergraduate students, and you have just 4 year senior year courses remaining. So this is an important announcement. If there are any undergraduates right now here, I'm not sure, but this is my announcement. Otherwise, I will talk with your advisors and tell your case. So another reminder, this is the first assignment. Actually the website, the Turnitin assignment, not Turnitin, but the assignment is on ODTÜ class right now. If you are done with the tutorial, if you have already done with the tutorial, you can simply upload your screenshots or certificates into this assignment. And as you know, the deadline is this Sunday midnight, and it will be 10% of your first mini project. And I will announce the first mini project probably at the weekend and give you about 2 weeks to complete this mini project. Another thing, if you have questions during my lecturing, please unmute yourself and ask your question, okay? You may also write into chat area, but it may take some time. I may not see it directly, so it's an urgent question. Please unmute yourself and ask it directly. So we started, some of you already know, start discussing the proofs on Thursday, and I forgot to record it. So I will quickly go through the first part and then continue with the rest of this chapter. So first of all, what is a proof? It should be a valid argument, and it should establish the truth of a given mathematical statement. So if you will follow a kind of a sequence of operations and then come up with a conclusion that the initial statement is true. So during this sequence of operations, we will be using some hypotheses. We may be using some axioms, which are kind of assumptions, and they are assumed to be true, obviously, these statements. And we can also use some previously proven theorems, some simple theorems, some mathematical theorems. We don't need to prove them once again. We can directly use them in our proof. So he said that it's highly important, especially in mathematics, as you know, and also it's important in computer science, since there are different algorithms and they should be valid for all cases. And you need to prove the given algorithm is valid for any, let's say, set of inputs. And let's discuss some more terminology. The theorem is the top one. It's the statement which is shown to be true. And in the proof, as I said, we will be using different, let's say, statements, different axioms, and axiom is one of the simple ones. It's a kind of an assumption, and we are assuming simply that these statements are true. Sometimes it's also called postulate, but we'll be using the term axiom. And during the proof of the theorems, you may come up with some true statements, and they might be some intermediate steps, and we call these statements, the true statements, as lemma. They are kind of theorem, but not as important as the main theorem we are trying to prove. And another similar term is corollary, and it's also again a kind of a theorem, and it can easily be proved or can easily be obtained from the available theorems. So you don't need to work much on the corollary. If your theorem is already proved, then the proof of corollary will take just maybe 3 minutes or just few statements. So how we are going to prove these theorems? We'll be using these axioms, some kind of definition, some previous theorems, some mathematical facts, some science facts. So there are different ways. We have direct proofs and also indirect proofs, and the rest, these four actually, let me mark here. Yes. These all are indirect proofs, okay? The first one we will discuss is the direct proof, but the rest is not an example of direct proof. We will be going through proof by contraposition, proof by contradiction, proof by induction, and recursion. These four are examples of indirect proof approaches, but the first one, the most straightforward one, is called as direct proof. And on Thursday, I think we just covered the first two. Now I will go through them once again, and then probably we'll have time and we'll be going through the rest of the indirect proofs. So first of all, in all the proofs or in all kind of theorems, we have statements. We have conditional statements. What is that? Here, as you see, P implies Q simply. And this means that if P is true, then Q should be true. And by using, as we mentioned, some axioms, some previous theorems, proven theorems, we should prove that this initial statement is true, which is P implies Q. If P is true, then Q should be true. So in our operations, in our, let's say, steps, we will use simple, actually, rules of inference. And at the final step of our, let's say, sequence of operations, we will conclude that Q should also be true if P is true. So this is quite simple, straightforward, the direct proof. You simply follow some operations, mostly mathematical operations, and then simply conclude that the given statement, which is P is true, if P is true, then Q is true, is true. But sometimes you may come up with a dead, let's say, step, and you need to start from scratch. This happens sometimes, or in some cases, there will be tricky, let's say, steps. So if you don't have, let's say, much knowledge in that field, it might be quite complicated. So you should really increase your knowledge in this area. So here are some examples. We started with a simple one. This is if n and m are odd integers, then n plus m is even. So I will simply redo this one, but I'm not going to spend some time on the remaining ones. So we said that this is our Q statement. Oops, not Q statement. This is our, obviously, P statements. And this is our Q statements. So how we start? We start by writing the, let's say, P with mathematical equations, n and m are odd integers. Then we can say that n is equal to some number plus 1, and m is also equal to some number plus 1. So then we can go to the next step and try to obtain Q, which is n plus m. And as you see now, if we sum these two expressions, it will be equal to k plus l plus 1. And we can easily say that this is an even number. So now we are done with the proof. The initial statement is true. We can say that P implies Q. Yes, this is another statement. We did prove it on Thursday. Some of the rational numbers is rational, so you can write rational numbers with some, let's say, letters, and then sum these and see that the result is also a rational number. Another one, if n is an odd integer, then n squared is odd. It's not that complicated. If n is an odd integer, then you can simply write it as n is equal to, let's say, 2 times k plus 1. And then if you simply take the square of the expression, you will come up with a statement that it's also an odd number. Another one, if m and n are both perfect squares, then that means they are squares of some numbers. Let's say m is equal to a squared and n is equal to b squared. Then our Q statement is the multiplication of these two, let's say, numbers is also perfect square, which means that a squared times b squared should be a perfect square, and we can easily put the square to the parentheses of a times b, and then you will easily see that the multiplication of m and n is also a perfect square. Any questions, guys, about the direct proofs? As I mentioned, you can simply unmute yourself, or if you have problems with, let's say, microphone, your mic, then you can write it into the chat area. If you don't have, then I assume that everyone is comfortable with the direct proofs. So we said that sometimes it might be a problematic, let's say, approach, and you may come up with an dead end, which means that your initial, let's say, maybe approaches, some intermediate steps are not fine. Then that means you should start the proof from scratch and try to use different, let's say, axioms, different theorems, and try to prove it. If it's obviously a true one, but if it's not a true statement, then for every, let's say, trial, you'll come up with a dead end. So this is not a straightforward, as I mentioned. Sometimes you may not find a direct proof way. If that's the case, then we can use indirect proofs. And indirect proofs, there are 4 of them, and at the end of it, we should again satisfy this statement. For each x, p of x should imply q of x. So this is the first one, proof by contraposition, the first type of indirect proofs. As you see, this time what we do in the initial step, this is our original statement, and we simply convert it to a different statement. This is called the contrapositive statement. We simply take the negation of this initial statement, we replace the order of P and Q, and also we negate them. And finally, as you see, we obtain such an expression. So negation, negative of Q implies negative of P is true. So once you do it, then the rest is the same with the direct proof. So what do? You write this contrapositive statement and then prove that this contrapositive statement is true. Once you are done, then that means you have proved the initial original statement. You don't need to do any other things. So again, as I mentioned, after you have written this contrapositive statements, we can, as in the case of direct proofs, we can use axioms, some other definitions, previously proven theorems. It's all exactly the same as with the direct proofs. So here is an example. If n is an integer and the summation expression 3n plus 2 is an odd number, then we state that q is an odd number. Let me do it, but I'm not going to do the rest of it, rest of the examples. So our original expression. This is P, and the remaining, this part is Q, and is an odd number. So what we are going to write, we should find negative of Q, which will imply negative of P. So what is the negative of Q? N is an even number. In the original statement, it's an odd number, but in the negative of this expression, in the contrapositive statement, it should be an even number, so I can write that N is an even number. So what about my right-hand side? This time I will negate the original P statement, which is stating that the summation expression is an odd number. So if I negate it, then this expression, actually 3n plus 2, should be an even number. Again, it should be something like 2 times some value. So what we are going to do, we will simply put this initial expression. Now this is our contrapositive statement. At this point, you should forget about the original statement. It doesn't actually an important issue at this point. We will simply concentrate on the contrapositive statement and then use again axioms, some simple definitions, some simple theorems, and then try to come up with a conclusion that this negative of P is a true statement. So what we do, we simply put this expression into here. So this means 6k plus 2. If you take this into parentheses of 2 once again, so this will be 3k plus 1. And I can say that this expression is an even number, right? So what I can also say is that L is equal to 3k plus 1. It's not important, but if you want to do a correlation or relate this final equation with your initial expression, you can also state that L is equal to 3k plus 1. Any questions, guys, about this example, this proof by contraposition example? So it's up to you. If there's a question about the type of proofs, how can we understand what we use, what type of actual proof we should use? It's about your experience. If you're an experienced, let's say, guy in mathematical science or computer science, and once you see the statement, you may know exactly which type of proof will be easier. But it's up to you. We don't have an exact answer for your question. Once you are experienced, it will be easy, but once you are inexperienced, then you may try some of them and then come up with the best one. Let me use this part, okay, and then escape, yes. We have another example, but as I mentioned, I'm not going to cover it again. On Thursday, we have done the, let's say, solution. It states that we have a multiplication A and B is equal to N. This is our P statement. They are both positive integers, and our Q statement is A should be less than or equal to square root of N, and or, this is important, we have an or statement here, B should be less than or equal to the square root of N. So what is our negative of Q? Since it's an or statement, its negative is this time an N statement. Since or implies that either of these is this is true or both can be true. So if you take the negation of this statement, then in that statement you should have A and B greater than square root of N. By using that expression, you can simply multiply A and B and come up with a conclusion that is greater than N, which states that N is not equal to AB. Since we have proved that the negative of P is true, we can say that the original expression is true. So if you don't remember it, please go through this example. Otherwise, you may have some problems in the upcoming more complicated, let's say algorithms, more complicated theorems. Another one, if n is an integer and n square is odd, then n is odd. Again, you can follow the same approach, same scheme. You can write the negative of q, write the negative of p, and then try to prove that contrapositive statement. So now this is actually done for the contraposition. Now we can jump to another indirect proof, which is contradiction. So this is totally different than the previous one. It's again an indirect example, but here what we do, we try to find a contradicting example to the original statement. We have a statement, and if you find a contradicting statement, then you can easily say that the initial statement is wrong. So in contradiction, let's say type of proof, we are trying to prove that the initial statement is wrong. So this is again our original statement, P implies Q. So what we do here, since we are trying to show that it's a wrong statement, we simply have a new contradicting statement. If this is true, then this should be false, right? P implies negative of Q. So initially, if you assume that the original statement is true, then the contradicting statement should obviously be a false statement. So if you somehow show this one, then we can say that show this one is wrong. We can easily say that the original statement is true. Here we go. We have an example here, a simple mathematical expression. This is our P and this is our Q. What P states is that 3 times the multiplication of a number x is equal to the number itself. Okay? If this P is true, then we only have a solution. What is that? X should be equal to 0. Since we don't have any other solutions, right? It cannot be one other numbers. It's not possible. It can only be equal to 0. So this is our original statement, P and Q. Now we are going to prove it by contradiction. So what we need to do, we need to first write this contradicting statement. P implies the negative of Q. So what is that? Then if the claim is wrong and if your P is true, then it should be the Q side is changed with the statement. X is not equal to 0. Okay. And then now we continue with some definitions, axioms, proven theorems. What we do now, we can simply divide both sides by x, and we can easily do that since in our new statement, in our contradicting statement, it's written that x is not equal to 0. So we can easily divide this both sides by x. So now this is the result, right? 3 is equal to 1. But obviously, this is a contradicting statement against our existing knowledge in mathematics. So we can say that the original statement is proved. So in summary, what we have done, we obtained a contradicting statement and we have shown that this is wrong. Which actually, once you prove it that it's a wrong statement, you indirectly prove that the original statement is true. It might be a bit complicated, but if you follow the, let's say, steps, you should easily do it. So in summary, we have original statement, P implies Q, then we write a contradicting statement, P implies negative of Q, and then we try to show that this contradicting statement is wrong. If you are successful, then you can say that the original statement P implies Q is a true statement. So another example, there is no positive integer solution to this equation. X squared minus y squared is equal to 1. So how we are going to proceed now? If we are using proof by contradiction, then we should have an if statement. Then if the given claim is wrong, which means that actually we should find a positive integer. Since in the original statement, it's written that there is no positive integer to the solution of this equation. So in the wrong claim, you should find a kind of positive integer set to this expression. So now let's proceed. So if you rewrite this actually expression in such a form, you can easily see that there is not such a set of integers which can satisfy this equation. Okay, that's why we can easily say that the contradicting statement is wrong and the original statement is a true one. Another example for proof by contradiction, we have kind of integers a and b. Their summation should be equal to or higher than 15, and this will imply that a or b should be greater than or equal to 8. So simply, if the given claim is wrong, then we should find some solutions for a and b where they are both integers and smaller than 7. So if that's the case, if they are smaller than 7, smaller than 8, I'm sorry, you cannot obtain 15 when you simply sum them together. So we can say that the contradicting example is wrong and the original statement is true. That's how we do it. So I think we will just stop at this point on Thursday. Our claim is now square root of 2 is an irrational number. So how we are proceeding, since this is an example for proof by contradiction, we should have an if statement, which is a contradicting statement to the original one. The original one is square root of 2 is an irrational number, so the contradicting statement is simply square root of 2 is a rational number. So what happens if it's a rational number? Then it should be, you should actually obtain it by dividing two integers, right? Another important thing is that these two integer values should be relatively prime, okay? Another thing, q shouldn't be equal to 0. So then what we do, we simply take the square root of both sides, and then we have a new expression, 2 times q squared is equal to p squared. So I can simply say that p is an even number. So how can I say that, or how can I have this conclusion here, this intermediate conclusion? How did I say that p is an even number? Can anyone tell me why p is an even number? You can unmute yourself or write into chat area why. I can simply say that p is an even number by looking at this expression. There's a p on left hand side, but this is a square expression, not simply a p expression. And other answers. There's another, yes. Squares of odd numbers are always an odd number. Actually, we had proved it in the previous direct proof examples. So that's why we can simply here say that p should be an even number. It cannot be an odd number. So let's proceed. Now we have the knowledge that p is an even number. So if p is an even number, then I can say that, let me write here. Here I have an intermediate step which is not written. Actually, P is equal to 2K. So I can simply continue with the remaining. If I take the square root of both sides, P squared is equal to simply 4 times K squared. Then if you go back to, let's say, Q, where is Q? Yes, here is Q. Why I can write such an equation, or how can I write such an equation? I simply use these two expressions. P squared is equal to 4K squared. So I simply write, actually, let me write it here. Oops, where is my pointer? Yes, here I go. It's equal to P squared. So I use this expression here and come up with another statement. So if you do some simplifications, you can easily see that Q squared is equal to 2 times K squared. So I can say that Q is also an even number. So what do you think? Are we gonna conclude something, or do we need to have more steps? So since in the axioms, in the earlier axioms, we said that these are relatively prime and Q should not be equal to 0. But if you check the steps, the results of steps 3 and 5, we conclude that P and Q is an even number. They are even numbers. If they are even, then we can easily say that they have a common factor of 2, which is contradicting with our one of the initial axioms. So we can say that the assumption is incorrect, and now we have proved that the contradicting statement is not true, which means that the original statement is a true one. So I can simply say square root of 2 is an irrational number, not a rational one. There's a question: if P is integer, P also must be even. Yes, they are integers. I couldn't get it right. If you're not comfortable, please ask it once again, or you can simply Talha unmute yourself and ask it. So if not, we have a quiz, guys. Right now, please simply log into socreative.com, okay? Select login and then select student login. This is the name for the room. Please write your answer and then do the quiz, okay? You have about, let's say, 5 minutes. Now I will simply start the quiz on the browser. Yes, now it's started. You can, as I said, simply open the web page of socreative.com and then log in as a student and then write the name of the room, the classroom, and then simply write your name and start the quiz. It's just a single question on the quiz. You need to write your explanation, so you don't have any multiple choices or matching type of questions. It's a small answer, a short answer question. Okay, good. Most of you have started the quiz. There is just a single student who didn't start it yet. Who is that? Anyone having problems in logging to SoCreative? Or is the student sleeping right now? So you have about 2 to 3 minutes left. So you're about last minutes, maybe more than that.
Hocam benim bir sorum olacak, sorabilir miyim?
Yes, go on.
Should we note this room name to a paper or something for further quizzes, or
I may change the room name, but right now you may note it. But I plan to change it, and I may use different platform, not always the same platform.
okay?
So you have just few seconds left. Please submit it. So I'm stopping the quiz now. Okay. Okay, guys, do you have questions before we proceed with the remaining of this chapter? Okay. Now we are done with the two types of indirect proofs. Now it's time for another indirect proof method. This is called as proof by induction. And this is a kind of special case. So once you see the statement, you will easily understand that you should use proof by induction methods. since they will be quite straightforward and quite obvious. Here are some schematics or figures showing this type of actually proof. For instance, if you look at this ladder, our statement about this ladder will be like this. If this guy is actually can move from step 1 to step 2, I can easily say that it can climb up to the infinity or climb up to the top of this ladder. And this is another illustration of proof by induction. If, let's say, this first domino falls on the second one, then we can say that the second one will fall onto the third one will fall onto the fourth one, and this goes to the end of your, let's say, set of dominoes. So this is quite straightforward, but we will have a mathematical approach. We will follow these approaches and try to prove the initial statements. So as I mentioned, this is a bit specific, let's say, case. The initial statements will be about the natural numbers. And you have a statement and it should be true for all the natural numbers, which are start from 0, 1 to infinity. And we will have some one-to-one correspondence, and we will make use of these, let's say, relations and try to prove this initial statement. So how we are going to proceed? We should first prove that the initial, let's say, initial statement is true. Not the initial, maybe. The statement is true for the first sets. If you look at here, for instance, we should start the proof by working on this first part. Or if it's a domino, then we should prove that the given statement is true for the first two dominoes. So after you prove that the statement is true for the first numbers, let's say, set, and then what you do, you simply prove that the statement is also true for another set of, let's say, numbers. Here we go. So these are the steps written in the correct order. We write the basis statement, and for most of the time it will be equal to 1, but there might be some specific, let's say, expressions where n is starting from 3 or 2. It's up to the statement. And then what we are assuming is that we are assuming that the given claim is also true for any integer which is higher than or equal to 1. And then what we do, this is the most critical step. If you cannot show this step properly, then you cannot prove your original statement. We should somehow prove that our statement is also true for n plus 1. We will see some examples, and I think it will be much clearer. Later, if you prove it, then you can simply conclude that the original statement is true for all the values of n. So this is actually what I mentioned. If you look at this domino example, if the first domino falls, then the second one will fall. This is our basis, let's say, statement. This is the basis, and the basis statement for domino example is here. The first domino simply falls. And the induction step, this is actually the induction step for domino. When a domino falls, the next one also falls. Okay, this is simply an example of proof by induction. So let's work on some natural numbers, some examples about natural numbers. Here's the first one. You see we have some odd numbers starting obviously from 1 up to 2n minus 1. And it states that the summation of these first n positive odd integers is equal to the square of n. So what is our basis function, basis statement, not the function, but the basis statement? If you remember, we should check whether the given statement is true for n is equal to 1. So if n is 1, then what will be our statements? Let me Yes, here we go, and it's equal to 1. And what will be the statement? If you put 1 here, 1 minus 1, 2 minus 1 is equal to simply 1, right? 1 is equal to 1 square. This is okay. The basis statement is true. Now I can proceed with the second step. I need to show that this is also true for n plus 1. So this is our original statement, and we should also prove it for n plus 1. So how we are going to do, we will have one more, let's say, a number. In the n plus 1 case, you will have another, let's say, odd number. What is the next odd number? What is that? Simply 2n plus 1. Okay. And then what will be the result? Since this time n is equal to n plus 1, we should take n plus 1 square, right? So this is how we should proceed. And if you show that this is true by using the previous, let's say, expressions, then you can easily conclude that the original statement about the natural numbers is true. Clear it? Yes. This is what I'm written. So how can we proceed? We can simply write a detailed expression for this one, which is n squared plus 2n plus 1. And then we can do some, let's say, these will be cancelled. And you can easily see that we only have the original statement. Since we were assuming that this was true, and we obtained the same one, so I can easily say that the given statement is also true for n plus 1. Then that means we are done, and we can easily say that this claim is a true claim. So this is what is done actually there. You can write it in various ways, but the idea is the same. So now here's what is done here is that we write this part. Let me go back to this one. Yes, this is the final expression for n plus 1, okay? And I can say that this part is equal to n squared. It's another way of doing the proof. I've done it with a bit different approach a moment ago, but in the slides, it's doing a bit different. This expression is equal to n squared, okay? So if you simply write it here, n squared plus 2n plus 1, and you will see that it's equal to exactly this value. So this is done here, and you can now say that the initial statement is proved, and you can simply say that the basis is true, and the conditional statement, which is implying once P of n is true, P of n plus 1 is also true. This is the induction step. And we have shown that this is also true for all positive integers. And finally, we can say that the given function, the initial function, which is P of n, is true for all the positive integers. And we have used the fundamentals of mathematical induction, or proof by induction. Here's another example, guys. Again, we have positive integers, or natural numbers, I can say. K is greater than 0, which means that our initial, let's say, basis function should start with, where is my, okay. We should start with k is equal to 1, since here it's written that the given statement is true for values of k greater than 0. So the first number is 1. I check whether this base is okay or not, and we can see that this is okay. And we can continue with the induction step. So we need to simply show that the initial statement is also true for k plus 1. So we are assuming that the statement is true for k and trying to show that it's also true for k plus 1. So here what we do is simply add one more integer here, which is k plus 1, and then we have another, the same expression on the right hand side. So if you look at this part, this is equal to the expression for k plus 1, and if you do the summation here, we can obtain such an expression which is equal to the right hand side of this part, the original statement for k plus 1. So if you simply use k plus 1 here, what will be? It will be simply k plus 1 times k plus 2 divided by 2. So I simply use k plus 1 instead of k here. So if you look at the final expression, we are summing k plus 1 with the right hand side, this part, and we come up with the same expression. So I can say that this claim is true, and we can continue with the remaining part of the proof and simply conclude that the original statement is true for all k values greater than 0. So let me finish this part and then we will have the break. Now, I will briefly go through the guidelines for proof by induction, mathematical induction. So what we need to do, we need to first write the statement, and the statement should be true for some n values, and it shouldn't be just some specific numbers. It should be true for all n values. And you may have some starting value. If this is an equal sign, greater than equal sign, then in your basis function, you should show that your expression is true for n is equal to b. So this is here, it's written in the basis step. We should prove that p of b is true, and then we will be done with the first step, the basis step, and then we will continue with the induction. If you're remembering from the previous examples, you should first assume that your, let's say, function for any k value is true, and then later show that your function is also true for k plus 1. If you somehow prove this one is true, then you'll be done. The rest is not important. Once you prove it, you can easily say that the original statement is true, and it shows that the initial expression for the natural numbers is stating correct, let's say, information. Yes, p of n is true for all the integers starting from b.